Hey, chemistry students, Mr. Ferguson here.
And Mr. Hunter.
And what we're going to do is look at another physical property that matter has, and that would be the property of solubility. So our objectives today are, first of all, to learn some of the terminology that we use describing solubility in solutions.
The second one is to learn factors that affect solubility.
And we're going to look at how to read a solubility graph, also known as a solubility curve. So when we refer to a solution in chemistry, what we're really referring to is a homogeneous mixture.
Homogeneous mixture.
And it can have, has to have at least two substances in it to be a mixture. It could have more, but if it's a homogeneous mixture, it's a solution.
Alright.
So usually we talk of mixtures having two parts, or homogeneous mixtures having two parts. And the first part would be the solvent. This would be the part of the mixture that does the dissolving. And of course, Mr. Hunter, we all remember that dissolving is what kind of a change, physical or chemical?
It is a physical change, unless of course we'd had our lab with the salicylic acid, which we needed the presence of sodium hydroxide to chemically alter the salicylic acid first.
Yeah, right.
So it would dissolve.
And then when it dissolved, it wasn't salicylic acid anymore.
It was something else. So that reaction allowed it to dissolve. Alright, then we have a solute, which is what, of course, if one does the dissolving, the other one is probably the one that gets dissolved. So let's take a look at this picture down here. Maybe. There we go. And you gotta... No, hold on, folks at home. Having technical difficulties. There we go. Bring to... Or not. There we go. Alright, see, we're learning. Alright, so here we go. So we have a picture of a solute, a solvent, and a solution. So Mr. Ferguson, of those three things listed there, which one do you think is going to be the solvent?
Well, when I make the copper sulfate solution, I start by figuring out how much water I'm going to need to dissolve my copper sulfate. So I'm going to say water is the solvent.
There you go, the water. Water is traditionally a solvent, which would make the copper sulfate or cupric sulfate here, or solute. And this means the last thing here, even though that says it's copper chloride, which it is copper chloride, it's just...
I got the wrong chemical.
You got the wrong chemical off the shelf. Doesn't matter, they're both blue solutions. So this here would be the solution. Right there, that would be your solution.
So when we discuss the different kinds of solutions we can make, the most common one that we think of is solutions which are liquids.
Yes, liquid solutions are what we deal in our everyday life. We drink them, we, I guess, freeze them.
Our cells contain them.
Yeah, so it's the most common that we're used to seeing.
So in a liquid solution, the solvent is obviously a liquid. And we kind of get... water-centric when we talk about solutions, like water has to be the liquid, but we know that's not the case, right?
But water, or H2O, is a common solvent.
In fact, I would argue it's probably the most common solvent.
It is the most prevalent, but anything can be a solvent. You can have ethanol, isopropyl alcohol as a solvent, as long as it's the more prevalent or the more abundant liquid that is being intermixed, that would be considered your solvent. So anyway, and then the solute then can be what, before we get off topic?
So the solute, we can really consider the solute to be anything that we can get to dissolve in the liquid. So obviously most often we're thinking of solids.
Most often like salt water. The salt is a solid and then it dissolves in the water. So there's one type. What else can it be?
So the solute can also be another liquid, which is what you were just referring to. We can take some other liquid, say isopropyl alcohol and
Dump
mix
it
it
in
with
and
the
mix it
water
together,
and
yep.
dissolve it, and we still have a liquid solution. But now the solute's another liquid.
Yep.
And Mr. Hunter, I'm going to throw this one to you. What's the third kind of solution?
Well, we already touched on 2 phases of matter, solid and liquid. It leaves us with 2 more phases of matter, but the most common of those 2 would be a gas. So I'm going to assume a gas would be the other type of matter that can be dissolved into a liquid. So let's take a look at the 3 pictures on the bottom down here. First picture here you see is isopropyl alcohol. Right there, isopropyl, and this is H2O. So, Mr. Ferguson, if I have isopropyl alcohol, I'm only going to say pour in 10 milliliters of isopropyl alcohol into my water. What kind of liquid solution is this going to be? Is it going to be one containing a solid, a liquid, or a gas?
Well, it's obviously a liquid dissolving in another liquid, and in the case that you said, since there's a lot of water, I mean that flask appears to contain probably 500 or 600 milliliters of water.
Yeah.
And I put 10 milliliters of the isopropyl in there. Water's the solvent. It's the most
majority
abundant
molecule,
liquid.
so it would be your. There we go. And looky there, it's even shrinking correctly. Here's another picture we have. There we go. You can see there's a powder next to the same round bottom flask of water. Let's say I dump that powder in to my flask and it dissolves. So what type of solute do I have now? Solid, liquid, or gas?
So it's a solid solute. And
Yep.
the solution will still be a liquid because our solvent, our water, or whatever our solvent was a liquid.
Yep. So here's more water. So that's our solute, and here's our solvent. And shrink that. And here's our last one.
This is Mr. Hunter's, one of his favorite kinds of solutions.
Well, yeah.
He likes the fizzy carbonated beverages, as many of us do. And
So right
what we're seeing
here, that is a foam or fizziness of your soda, which would imply we dissolved what into our soda, into our liquid?
some kind of gas was dissolved, and in the case of soda, that's going to be carbon dioxide.
That's absolutely correct. So that's an example of a gas being dissolved in a liquid. So we can have 3 different types of matter dissolved into a liquid. Let's move on to our next type of solution.
All right, so the gaseous solutions, the gas can be a solvent. So
Before we get too far, here's our picture of our next solution right there. It's nice, isn't it?
there's nothing in there, Mr. Hunter.
Well, we need to invent the molecular goggles. We'll find out what's in there. So anyway,
That's right. Yeah.
molecular goggles. That's what we need to invent still. So our solvent is going to be what if we're talking about gaseous things?
It's going to be a gas.
Yes. Which means our solute was also going to have to be a what?
A gas.
A gas.
Gas.
They're pretty restrictive on who their members can
That's
be.
a pretty exclusive little club.
Yeah. They don't like solids or liquids to be up there.
You've got to be in the gas
Phase,
family,
yeah.
the gas phase to join them.
All right. So
Obviously we know with our molecular goggles on, in that first picture we're looking at
yep.
some air inside
Yes.
there.
And inside that air, I should say, is composed of right over here.
Quite a few gases there. What do we see?
Yeah, so we know it's nitrogen, 78% nitrogen, so that's probably going to be our solvent, correct?
Correct. The one
So-
that's the most abundant gas is considered the solvent, and all the other gases are dissolved in
Yeah, so these
the solvent.
here are going to be our solutes. So those are the ones that are being dissolved. This is a good example of one solvent with multiple solutes. I mean, as you see there, it says other gases, 0.03%. So, I mean, it's
Those
obviously...
other gases are all
Yeah,
sorts of things.
helium, hydrogen,
Right.
sulfur
Xenon,
dioxide,
krypton,
xenon.
radon.
Exactly. So there's hundreds of things dissolved in the atmosphere, gas phase wise. So there's a good example of a gas phase solution. Anything else we need to talk about for this one?
Now let's move on to solids.
All right, on to solids. All right. So our next type, as we were talking about, is a solid solution. So if it's a solid solution, that means our solvent is going to be
A solid.
A solid. And Mr. Ferguson and I are having a hard time thinking of anything that a solid could dissolve that's not also a solid. So, if you come up with anything, bring it in and tell us, and we'll reward you with a solid solution known as hard candy. So the solute, we believe, is only going to always be a solid, but if you come up with something, we would like to be proven wrong.
We're not sure on that one, but what we are sure of is these are homogeneous mixtures too. You know, when we say the word solution, we always think of, you know, some kind of blue liquid in a beaker in science class, but it can just as easily be a gas, as we saw in air.
Yep.
It can just as easily be a solid, as long as it's a homogeneous, uniform mixture.
Exactly.
It's a solution.
So pictured to the right here, we brought out a piece of metal. This here is brass, which is composed of, so this is brass, which is composed of copper and zinc. Now, I don't know which one's there in higher proportion. I think there's more copper than zinc in brass. So I would think copper.
Let's just go with that. Let's say that the copper makes up the higher proportion of it.
That means the copper would be the solvent, which is odd to think of in a solid, which means the zinc would be your solute. And that covers the types of solutions that we want to talk about.
One other question, in case someone's wondering, how do we get a mixture that's homogeneous and solid at the same time? So do we chop them up really small and just pack them into a mold?
If we did that, we would have a heterogeneous. I mean, we could chop them up small and then melt them so they go through a phase change. And once that phase change undergoes, you can then pour the liquids together. And then when they solidify, they'll solidify as a homogeneous new solid.
So that's, I'm pretty sure that's how they make things like brass.
Yeah, they just kind of do a giant blender and blend them. Well, stainless steel, I think, is galvanized. I'm not really sure. Anyway, on to the last thing. We're going to teach you how to read a solubility table. Well, right now we're going to talk about the factors affecting solubility, but first we need to define solubility. So, Mr. Ferguson, how would you define solubility again?
I'm going to say it's the amount of solute that you can dissolve in a certain amount of solvent. The maximum amount.
It's also the ability to be dissolved into something else, but yes.
So if we want to quantify it, we would measure the maximum amount of solute that can be dissolved.
Guess we could have left more space there, huh?
In an amount of solvent. An amount. Oh, I have an on there.
It's okay.
Amount of solvent.
All right, the first factor we're going to talk about that affects solubility is temperature. As temperature goes up, solubility goes up normally.
So I'm going to do this shorthand. Increasing the temperature leads to an increase in solubility.
For solids.
For almost every
gases
solid.
Are reversed.
Right. Gases, it's different, and you'll see that when we do solubility curves. But for just about every solid substance.
So we're going to write that down below. It's saying for solids, just so we know. Solubility. There we go. That's what we're normally going to deal with. We're not going to normally deal with gases, but just be aware of that. And then the last thing we're going to talk about real quick is polar and non-polar. It's a property we're going to hit later in the year, but we just want to throw it out there. So a polar substance will dissolve in another polar substance, and a non-polar substance will dissolve well in a non-polar substance. And the catchphrase we just want right now is like dissolves like. This will come into play later, and we don't really expect you to understand what a non-polar or polar molecule really is until later in the year. So remember, if once you're done writing here, write the words like dissolves like as well, if he has space for it. Alright, and now we're going to take a look at a solubility graph. Alright, we're going to look at some solubility curves. In the bottom right corner you'll see an actual graph, but before we throw you at that, we're going to talk about how to read these. So Mr. Ferguson, where do you want to start off with these so far?
If we took a certain amount of water, or any other solvent, but let's say we're going to have 100 grams of water, and we took a solute, like
Salt.
sodium chloride, and we measured the amount that we could get to dissolve of sodium chloride in that 100 grams of water at different temperatures. So maybe we took 100 grams of water at, way down here at 10 degrees Celsius. We could get, this much salt to dissolve. And then we went up to 50 degrees Celsius. We'd get this much to dissolve.
And then at 100, we can't get water any hotter than that.
100, or yes, because it's going to begin to boil, we'll get this much to dissolve. And you can see exactly what we were talking about on that last slide. As temperature goes up
For a solid,
solubility goes up.
yes. So this means you can now read this graph like anything else. If I were to say, how many grams of salt could we have at 25 degrees, you could draw a line up from where 25 would be at, and then follow it over to the y-axis, and there would be a number there for you to read. So now that we have a brief introduction of that, let's take a look at a real chart. There one is. This is one that has both solids and gases. The dashes line are gases. So notice the dashed lines are decreasing with increased temperature. This is why a lot of fisheries are where it's very cold. You can have more dissolved oxygen in cold water than you can hot. And that has to do with molecular motion. But again, that's not what we're talking about right now. So let's learn how to read this.
Yeah, all of the non-dashed lines are different solids, which dissolve just like the last one. So if we pick one, let's pick sodium nitrate here. Here's sodium nitrate.
Yep.
Okay, so let's say, Mr. Hunter, give me a temperature.
Let's say it's at 30 degrees Celsius.
Okay, so we want to know what the solubility of sodium nitrate is at 30 degrees. So we're going to find 30 degrees. We're going to go up here until we intersect that graph, and then kind of come over here.
And this would say we have about, what, 90?
I'm going to say 93, almost 93, 94 maybe, grams of solubility.
Per 100 grams of water.
That would be the most you could get. That line represents the ceiling, the most you can get to
which
dissolve.
Is known as the saturation point.
Right, so we would have a saturated solution, that is one holding as much dissolved solute as we can. And you notice that there's a different curve for each different substance. That relationship we looked at only applies to dissolving that substance in water. If we were to switch to, say, potassium nitrate, we have a very different solubility curve.
Actually close, though. It would turn into...
It's much steeper.
Yeah.
And at the solubility at 30 degrees for potassium nitrate, now we are, about right there.
Which is only about 48.
48 grams of potassium nitrate dissolved. So we're going to give you lots more practice in class interpreting this kind of a curve, but this is what you need to get used to looking at for solubility.
All right, and we're going to take a little bit more time on one more slide to talk about three terms that we kind of just used, so bear with us. All right, so we have three zones to talk about. We have the saturated, supersaturated, and unsaturated. Those are the three definitions we're looking for.
We're looking at a solubility curve here for a random substance. It doesn't really matter.
Salt. It doesn't really matter. So
okay, so if we dissolve an amount of salt at a given temperature that is less than that line.
Yeah, so if we're underneath the line.
If we're underneath the line.
That's unsaturated.
That means that there's room at that temperature for that solvent to hold more solute. You could go up higher.
Add more solute. There you go. Can add more solute.
There's room to dissolve more at that temperature, anywhere under that line.
So what happens if we're at that line then, Mr. Ferguson?
If we're at the line, we are at what's called the saturation point.
Saturation point.
And if anywhere on that line at that combination of solubility and temperature, the solution is saturated, which means it's holding the maximum amount of solute that amount of solvent can hold.
And then the last point, max solute for that temp.
Now, you might think that's the end of it, but actually you can kind of trick the solution into going above its saturation point.
Yeah, right up here.
What we would do is heat it up and make a saturated solution at a hot temperature and then cool it off. So we'd actually be on the red curve there, and then lower the temperature slowly, and if you lower it slow enough and you have clean glassware, you can end up in the region where Mr. Hunter's writing right now. That's called a super saturated
holds
solution.
more solute than the temp and solvent. That's pretty bad,
So
right?
holding more solute than it should be able to hold at that temperature than it's theoretically able to hold it. And it's called super saturated. As you can imagine, this is an unstable situation.
Yes.
And anything can trigger
A cascade
effect.
If you remember those hand warmers I showed you in my class, that was a super saturated solution that had a clicker in it that caused these crystals just to cascade out of solution. And to make it go back to being a super saturated solution, I had to heat it in a hot bath, take it out, let it cool, and then click it. I'm sure Mr. Ferguson will show that demo here once he gets a hold of more, because he decided to boil his down into nothing on a hot plate and melted them. Yes, he did that overnight, folks.
We don't have to get personal.
That's for the hand model joke.
Okay.
All right, we'll see you later, students.